All right. Okay, welcome again, everybody, to our second round of the VMOL seminar. It's my great pleasure to have Abzer and Axel presenting today on our FBMN-STATS guide, and in particular, the web app behind that. And just to give you a very brief introduction, Abzer is a graduate student in our group. She studied biomedical engineering for her undergrads before she then did a master's in medical photonics and was a data-heavy background already. She's now doing her PhD in computational mass spectrometry. Axel is a postdoc also here at the University of Tübingen between Oliver Kohlbacher and Christoph Meyer, and Axel studied here biology before he also then went more into the computational and in particular computational mass spectrometry side, and now is developing OpenMS and fancy web apps, as you will see in a second. And yeah, without further ado, thanks for presenting, and I'm very much looking forward to the seminar.
Yeah, thank you. I guess everybody can hear me. Okay, cool. Thank you, Daniel, for the kind introduction. And hi, everybody. And today, me and Axel, we would like to present the FBMN-STATS guide that we've been working on since last year for the statistical analysis of feature-based molecular networking. As you can see here, it's not just like few people, but there are so many people whose work is involved, especially thanks to so many people from VMOL who contributed to this. So yeah. One second. Yeah. Okay, before going into the stats guide, I just want to give a short introduction. And so here, first, if you take into metabolomics, I don't want to go deep into it. I guess most of you already know. So with metabolomics, we already study metabolites, which are pretty much the end products of cellular processes, and with which we can already get overview or like a snapshot of what's happening in these biological samples. And unlike other like omics, such as genomics, transcriptomics, or proteomics, which already have these, which are advanced and which already have these really nice workflows. But with metabolomics, we do not have like that many like consensus with the workflows. Therefore, yeah, so from this, once you have your sample and you perform your LC-MSMS analysis, such as this liquid chromatography, tandem mass spectrometry analysis, where you have your sample and for which we get these MSMS spectra, which pretty much gives you your mass to charge ratio, retention time, and peak abundances for all these metabolites that are found in your sample. Whereas when you're doing these untargeted metabolomics, which is not focused on a particular metabolite, we pretty much try to cover a wide range of metabolites from your samples. As you see here, there are so many spectra here, where most of them are not annotated. A significant portion of them is kind of unknown. So yeah. So we would like to identify these features to improve these annotations. Particularly, we make use of this molecular network analysis in GNPS platform. And the one that we commonly use is feature-based molecular networking and also high identity molecular networking. So what happens here is the peaks, what you see here is these several MSMS spectra. So these MSMS spectra are clustered based on their spectral similarity, helping to build this MSMS networks. And it is based on cosine score similarity. So what happens here is that when you have two MSMS spectra, it overlaps it and sees if they are similar to each other. And based on it, it gives a score. When the similarity is higher, you get a higher cosine score, whereas when it is less similar, you get a lower score. And in this case, if you take this two MSMS spectra, when you have a precursor mass difference of 14, with this cosine score metric, it also allows you to go into look for these mass offsets in this fragment ion in the MSMS level as well. This is what we call as this modification-aware MSMS similarity. Daniel already mentioned about these in our introductory seminar before 2 weeks. So yeah, so as you can see here, you see this representation of domoic acid, and here you see this modified version, which is the carboxylic acid modification of this domoic acid, and they are nicely connected with each other in this molecular network. Not just the MSMS spectral similarity with advanced techniques, you could also go into look for similarity in the coelution profiles in the LC column, and here you could also match these spectra based on their retention time in MS1 level, and also based on similar ion addict. So once you have all these information with which you could build this molecular network, and you could propagate into this chemical space of your like your metabolites or your data, where you could see these nice clusters of carbohydrates, plasticizers, alkaloids, and as you can see, the color ones represent the annotated ones, whereas the gray ones are like pretty much the unidentified or not annotated ones. And with these molecular networks, it's a great tool, as you could not just look into their similarity or like these clusters of their classes, but you could also nicely identify or putatively identify the unknown compounds. So with this information about this molecular networking, what we do with our metabolomics pipeline is that once you get your data from your LCMS MS analysis, we perform enzyme-3, with which we detect the features. And once we detect these features, we go on to GNPS, perform molecular networking, which provides us a certain level of annotation. And with Sirius, you could also further improve your annotations. And with this wealth of information from enzyme-3, GNPS, we wanted to also simplify it for the beginners in order to perform their downstream analysis and understand their data better. Therefore, we developed this simple web app, FBMN-STATS. And yeah, here enzyme-3 and Sirius, they both are computationally intensive, and you could locally run it. And with GNPS2 and FBMN-STATS, both are available online. However, for beginners, you could use the GNPS dashboard, which nicely incorporates all these in the web, where you could visualize your raw data and do feature detection and also perform molecular networking. And you could also do FBMN-STATS guide in GNPS2 platform. And yeah. So the idea is that we wanted to build a workflow that is beginner friendly for the users to perform their downstream statistical analysis after feature-based molecular networking. With this aim, last year we started this work. It started as a simple one, but ended up into this huge work. So we wanted to provide this step-by-step guide in a protocol format, also provided with example scripts in popular programming languages, which you could use and modify according to your needs. And yeah, for those who are not comfortable with it, we have also provided this web app, which is the FBMN-STATS GUI. And in order to run this pipeline, you would need a feature table or feature quantification table, the one that you get out of the MZMine tool. As you see here, each row represents these samples that you run, and each column represents the features or the metabolites, and the values you see are the peak area abundances you observe for these intensities. And as you can see here, the samples could be of different types, as blank samples, QCs, controls, treatments, etc. And then the metadata table is something the user creates that can be easily created in Excel, where you have you define the file name as same as the feature table, and you add additional columns explaining what is in your data, such as different sample types, your different groups, and if you have replicates, time point information, and so. And with this information, when you run it in GNPS for molecular network, you obtain this annotation information, such as shown here. For each of these features, you also get the cosine score, as mentioned earlier, and the annotated the annotations. And similar such table can also be obtained from Sirius. So with these tools, you could run this platform. And yeah, Axel would also show this in a simpler way. You could also directly go with your GNPS molecular networking task ID. You could also run this this pipeline, where we also give information about how you can better prepare your data, from sample prep to feature table generation. And once you have these information, you first go with data cleanup, where we perform some preliminary cleanup steps, such as we remove the blank features or the background features, reducing the number of features already. As you know, with untargeted metabolomics, we have a huge number of features, and we remove these noisy features, and then we perform imputation, where we replace these zeros and missing values, and finally perform normalization and scaling, where we account for these biases between these samples. And then we can move on to perform multivariate statistics, where we perform unsupervised and supervised classifications, where one could do visualization, such as looking at the overview of your data in a lower dimensionality space, showing a heat map, and advanced supervised classification, such as random forest. And you could further deep dive into univariate stats, where you could perform parametric and non-parametric tests, where you could do hypothesis testing. And all these informations are openly available in our GitHub page, Functional Metabolomics Lab, where you could find the info in the FBMN-STATS repository. As you could see here, all these folders are, they're all folded, such as Python, time to R, and for the web app. And we have also provided the test data set. And yeah, it is also available in notebook format, in Jupyter notebook format, as seen here. And the notebook can be run in Google Colab version as well, in cloud platform, and it could also be just locally run. And for the people who are interested in installing it and running it locally, we have also provided documentation for this. Again, summarizing this nicely with this decision tree. So with this protocol, you can first start with reading this protocol, and based on your experience on your scripting language, if you do not have, or if you would like to learn, then you could just choose whichever platform you're comfortable with, Python, R, or like Chime 2. And based on also the size of your data set, if you have smaller data sets, you could just run the Jupyter Notebook on Colab environment. You don't have to install anything. It is just on the go. And if your data set is large, then it is preferable to install it locally and run it via Jupyter Notebook. And if you do not want to do anything with the scripting language, but just want to go with GUI version, then you could just go with the FBMN-STATS guide. So I'm not going to show any Jupyter notebooks today, as people would be much more interested to see the GUI, but I just wanted to show some screenshots of the Jupyter notebook. As you can see here, this is from the R notebook that we have provided in this protocol. You could see they're nicely structured step by step, where you have to provide inputs and what sort of outputs you would get for each step. And as you can, these are some example figures from the notebook, where you can see the PCOE after each steps, or like heat map. And with this, I also move on to the FBMN-STATS guide. This is the homepage. I don't know if it's been already shared, but I would also, Daniel, can you copy the link? And 1 second. I can also copy the link and share it, so that.
Don't worry, I can copy it.
Okay. I deleted it. But... So with this, I would just pass the stage to Axel. And Axel was kind enough to make this web app. So he would show us all now, walk us through the app version. Yeah, I would stop sharing so that he can share.
Yeah, thanks, Abzer. And hi, everyone. So for the second part of the talk, I would like to talk about, first of all, why we would want the graphical user interface and what's the background of the app. And then we will walk through the whole app. And yeah, I will just showcase what you can do there. And at the end, I will show you how you can contribute and bring in your own features. So why a graphical user interface and not just the notebooks or just the scripting command line interface tools? First of all, the accessibility and the low barrier to entry, of course, because we can't expect all people to want to code or know how to code. And of course, the data exploration aspect and the interactive plots are much better in a graphical user interface. So you can change parameters, you can click around in the plot, zoom in and hover and get much more information out of it. Also, if you have that interface, inputting parameters is much easier and more convenient. What's the web app for? It's for smaller data sets and where you want to do manual investigation, and also for a wide range of data sets. So not just metabolomics. You could also hand in any data that has features and samples and intensity values. And you could add metadata for them and yeah, do these statistical analysis with the app. What it's definitely not for, it's not for huge data sets and automated data analysis. So it has its limits. If it's really large, the data, then I would suggest that you do that in the notebooks. Yeah. So the technical background for the app, it's written in Python, and the base is Streamlit. That's a Python module that turns data science script into web apps, and that's really has evolved within the last years or so to be quite powerful, I would say. So it runs in the browser and it has a nice default user interface. You don't need to care too much about to style your apps or to where you place your widgets and so on. And I think for me, that's really nice because I like to work more on the back end and the functionality of the app and don't want to bother with putting too much work into styling the app. The input widgets are really convenient because you can have something for everything. You have a range of text inputs, number inputs, sliders, drop-down menus, everything. And of course, you can display interactive tables and figures. And also a plus is that you can host it for free and very easy on the Streamlit cloud. So they offer that. You can just link a GitHub repository and you can share your web apps very quickly with your colleagues, also prototypes, and do that in the Streamlit cloud before you might want to then host it on your own server. One important thing that you need to know if you want to develop that app is also pandas for handling the tables and data frames, and of course Plotly for the interactive figures, and all the packages that you might need for statistics and data analysis. Okay, so let's just jump into the app. So Ming was kind enough to host it on his GMPS2 servers. So we have that running not only in the Streamlit cloud anymore, but also, as you can see here, on FBMN-STATS guide.gmps2.org, which is pretty cool. And yeah, this is the welcome page that you get here. There's a quick start guide. Let's quickly walk through this. So important, all plots are interactive. And you can also save these plots. So if you hover on the plot, there's a camera icon in the top right corner. And you can select an image format down here in the settings panel. Yeah, to prepare your data, that's the only mandatory step that you have to do, that data preparation page here. So as Abzer has mentioned, we need two tables, the quantification and the metadata table. Here we support a wide range of formats like TSV, text files, CSV files, and also Excel files. And it's automatically detected what you will input here. You can also, if you want to name your features up front, you can put in a metabolite column. So you just name that column metabolite, and that will be taken as an index, or you can also detect that automatically. Yeah, what else? So important that your sample file names that have the MCML file name extension, and the quantification table, of course, needs the same sample file names as the meta that are also in the metadata table. And they should be in the file name column of the metadata table. Yeah, we have example data, various example data in the app already. And then you remove the blank features and impute your missing values in the data cleanup section before you can then jump into the statistics part. So there's just two examples of tables that you can use. And with that, I would say just go to the data preparation. First of all, the file selection. You have some options here like file upload. In that case, we upload these two tables manually. So let's do that real quick. So I have a quantification table right here. It will upload depending on your internet speed, and a metadata table. And as we can see here, we already get a warning that no metabolite column has been detected. So we have the option to create the index automatically from the MC, retention time, and row ID values. And as we can see, that's a nice, unique feature name that's getting generated. If we don't want to do that, we want to take any other column. We can also do that and select from the columns which have unique values. Yeah. So for example, right now, the row ID is the metabolite name. What else? So we can check our uploaded data here. We can also use the GMPS task ID. So if you have run a GMPS job, very convenient, just copy the task ID here. And you also get the option to annotate metabolites that you have discovered. So this kind of generic feature name will be replaced by the actual metabolite name, which is pretty cool. Then we have two example data sets. One is from the publication. That's also on GMPS, so that's preoccupied here. And when we run that, it will pull the data from GMPS, also annotate the metabolites, and then show the tables here. So as we can see, it already named the features, and we get some that have been annotated already. Okay, so that's the metadata for this one. So just as a hint, you don't need to put that attribute prefix here. You can name the metadata as however you want. It's not required anymore, at least for the app. But for the showcase, I will just put that small example data set for testing. And some of you might recognize that and know what it is. So we have only a few attributes here. We have actually the sample, which is more or less the same as the time point. It's just a string name for the time point. And we have the sample type where we can separate blanks and samples. So a very simple data set, but it's really cool for testing. Data cleanup is the next step. And in most of these pages, we have an about section where Abzer has made some really nice figures for the publication. You can check it out here. And there you will get some information what's happening on these pages. So to remove blank features, we will select our samples based on that table here. So we need an attribute and then select our samples. You can have a multiple selection here. For example, if I only want to contain the 15 and 5 time point samples, then I could do that. So we have selected 6 samples, 3 replicates each. Or I could put in more, and just to showcase what's happening if I put in all. So we selected everything, and therefore we can't add a blank sample. And warnings like these I have implemented on some parts of the app, just on some checkpoints where something might go wrong. And yeah, you already know what to do. You can just remove the process blank. Then we have our 12 samples and a huge number of features, or we can simply change to the sample type attribute. The same goes for the blank selection. Now there's only one left. It's pretty easy. And you can also check your selected tables right here. So it's only one sample that looks correct. Then we have defined a threshold for the blank removal. And if you're not sure what's happening on these steps, sometimes there's a question mark on the widgets and you can read what's happening here. So in that case, we define a ratio. So that's the mean of the blank and the mean of the samples. And if that ratio is above a certain threshold, then they are considered noise or background features. And if I change that, for example, if I make that less strict, then we get less number of background or noise features, of course. And we can also nicely see how that updates in real time, the number of features that's left after blank removal. Okay, so before imputation, I would like to show you the plots at the bottom here. So we have a feature intensity, a frequency plot, where we still have lots of features that have 0 values, and also the missing values per features. So most features have 0 missing values, which looks really good. And after we do the imputation, then that plot changes and updates. So we have no 0 values anymore, obviously. So the next step would be a normalization, the next mandatory step that we have to do. You can choose between center scaling and total ion current or sample-centric normalization, or you cannot choose to not normalize at all. And then don't forget to click on that button, submit your data for statistics. That will put everything together. And now you're ready for the statistics part. This is the final table that all the statistics tabs work with. So we have the normalized values and your metadata all in one table. You can download it, do whatever you want. So if you just want to use that for pre-processing, that's also fine. And if you're not happy with that, you redo that right now. Yeah, I would say let's quickly walk through the tabs here. First one is the principal component analysis. And here's really cool how to see interactively what's happening. We get the PCA clustering. When you hover, you can check out the names of the samples, and you also get the explained variance. So if we increase the number of components, we will quickly see that the first 2 components account for the majority of the variance here. And most of these have also tabs for data. So you can download that, all the data for the plots and recreate the plot in another tool, for example. For Permanova and PCOA, so we have multivariate statistics here. You can do that as well. And I think what's interesting here is if you check out the PCOA plot, when you change the distance matrix. So you can really pick one that suits your data, and some are not clustering like that. So that's pretty interesting. If you have the Euclidean, that's the same like the PCA plot. Okay, so here we have the clustering and the heat maps. Right now, that's not so interactive, but that could be if someone would like to add some stuff here and, excuse me, for example, would add like a colored bars here for showcasing attributes. Yeah, but you can download all these figures here ready-made as a plot. Yeah, and also the data. Next one would be a random forest. So here we can run the supervised learning and see which features are the most important for that selected attribute. And when that's running, you also get this out of bag error plot, where you can see the number of trees that you need in order to bring the error rate down. And that's just a table where you rank the features by importance after this supervised learning. That one is interesting. That tab is how you choose your statistical test. So for choosing a test, it's important to know if your data is parametric or not. So if it has normal distribution of values, or and if it has equal variance or not. And for example, yeah, it's the same, but if we choose the time point here and we are interested in that, and we want to compare specifically like some of these options, for example, the most extreme, 0, and the endpoint, then we can do that, and we can see the distribution of p-values here. And how you can interpret that, there's also a hint here, but basically, if it would be a normal distribution, or groups that are not normally distributed, that they have a significant p-value below 0.05, and then we will get a huge number of data points here on that lower side. If it's all evenly distributed, then we should expect like a flat distribution. The same goes for the equal variance plot, but data is not normally distributed if we get a large number here in that lower area, but it's not the case in that. Here it's not the case. Same for the variance. And then how we can interpret that, we can also extend the figures here. So here we can see it's normal distributed. Our groups, they are not paired and they are not dependent, and we want to compare more than 2 groups, yes, then we should do ANOVA and the subsequent Turkey's post-hoc test. Yeah, so let's do that. We can run ANOVA here directly, just select one attribute, and it will showcase all the features that have differ significantly in their variance. Oh yeah, and while that is running, we also have, you can choose the p-value correction method here for all your statistical analysis jobs. We currently use Bonferroni in the notebooks, and that's why it's the default here. So after running ANOVA, you get that plot with these values that you can investigate, and also as a table, of course, with the p-values. Sometimes the display is a bit weird because it shows 0 because it's a really, really small number. But if you download the table, it will be correct. Then you can investigate the most significant metabolites here, or the ones that are significant after correction, p-value correction. And you can check out all the different features interactively. Okay, so if we want to confirm, like for a special pair in that attribute, let's say we want to confirm that the most extreme values, 0 and 45, are actually different in that attribute for the significant features, we can run the accompanying post-hoc test. And yeah, that's just to make sure that we are on the right side here. And it also gives a plot like that, volcano plot here, where you have the difference, which are up-regulated, which are down-regulated. And you also get that as a table. We can skip the Kruskal-Wallis and Duns because that's more or less the same. You would choose that if it's not normally distributed. And then at the end, we also have the student's t-test, where you have some options. For example, you can do the pair test, or you can correct for unequal variance. You can choose if you want two-sided or not, and then simply run the test. Yeah, and if you have a huge data set, this can sometimes take a while, of course. That's why it's better if you have large data sets to do that automatically. But again, you get some outputs here. You also get the significance indicators in the plot of your metabolites. Yeah, which is pretty cool, I think. Cool. With that, we're at the end of that showcasing here. But I want to show you how you can contribute to the app if you would like to. So that's the GitHub repository, the link here. And yeah, that's how it looks like. That's the code. So you can fork it, create your own fork, and then make any changes that you want to do. And then open a pull request here. And we can merge that into the app. So for example, if you want a new statistical test, you can simply add that data here. Or if you want to modify stuff, do that. And if you have any questions, feel free to ask, and I will be happy to help you with that. Would be really cool if there are some more features and some more extended functionality. For example, in the notebooks, we have stuff that's not yet in here, just to make it more complete. So just as a hint how you could begin. So the data preparation page that results in 2 data frames, which then can be used in all other pages. And they are in these variables in the session state data. That's the pandas data frame with the imputed normalized intensity values. And then we get the MD data frame with the meta values. And that's all you need, basically. Then you have to put the GUI logic of Streamlit into the pages folder, and you can separate the functions where all the statistics and computations are run and put that in the source directory. And here are some suggestions for beginner tasks that I have collected. And by the way, thanks a lot for all that have reviewed the app or gave comments to that. That was really helpful, also fixing bugs and yeah, just improving it in general. So if you want to learn building these apps, it's really not difficult. You can use that as a playground. For example, what we can still add, that you have a new normalization option. So you do a tick and center scale normalization subsequently. You do them both. Or as I mentioned, the heat maps, they could use some more complex stuff, like you could have the meta values as colored bars on top. And that one is a bit more complex, but I think also possible. So for example, if you don't want to choose the pairs for the ANOVA and the Kruskal-Wallis test, the post hoc tests all by hand, then you could simply automatically calculate all of them and visualize that accordingly. That would be pretty cool. Or whatever you find useful. So any contribution is welcome to the app. And with that, I'm already at the end. So thanks to all of the people that have helped with these statistics stuff and the app and the notebooks. And yeah, I guess we're at the end of the talk and I can hand over to the questions. Oh, by the way, what I wanted to try and what's really interesting. So if some of you want to open that app here at once and just play around with it, that would be cool as a kind of stress test, so we can see how the GMPS2 servers handle that. That would be pretty cool.
Awesome. Well, thank you, Axel, and thank you, Abzer, as well. We actually already started stress testing this. Some of the students in my class know because like 10 of us logged on at the same time. So it's not 100 people, but it still worked. So anyways, it's awesome. We love it. But yeah, thank you everyone for attending. I guess I'll let those of you who have to go off to the next thing go and say farewell before we take any questions that the audience may have. So bye to those of you that have to leave. And then, yeah, if anyone has questions, now's your chance to talk to the developers.